Everybody, thank you to today's headline. We start with Xuening both of them are. So before that, he was in 2000 in ITC. He is mostly information and plasma physics, and I believe that this will.
Okay, thank you very much for having me, and thank you for coming. So this talk is about partly. Do I have a pointer or? Okay, thanks. Okay, thanks. So this talk is partly methodology, which I'm trying to advertise a new code that we have recently developed that combines MHD, grid-based MHD, with the particle-in-cell method, and partly science, where we try to describe some application of this code, in particular to the cosmic ray streaming instabilities related to the interaction of cosmic rays with the background thermal plasma. This is work in collaboration with Lorenzo Xuening, my office mate, together with a bunch of Princeton folks. So cosmic rays are energetic charged particles that are basically all over the space, and we have known cosmic rays for over 100 years with plenty of data, and basically the origin of the cosmic rays, how are they accelerated, and how do they escape from acceleration site, and how do they propagate through the ISM and beyond. Densities in rough equipartition with many other ingredients such as magnetic pressure and thermal pressure and turbulent kinetic. Cosmic rays may be an important contributor to driving large-scale galactic wind, such as in this MHD-2 starburst galaxy. And to address these questions, we would like to start from the basic level. Basically, how do cosmic rays interact with a thermal plasma? There are several ways that they can interact. From a very passive point of view, cosmic rays are they're essentially collisionless. Okay? And all they do is that they respond to magnetic fields. They can gyrate around the magnetic field, and if there are waves and turbulence in the ISM, they are scattered by this waves and turbulence. So that's the passive aspect. But there are also more active aspects that because cosmic rays are dynamically important in terms of pressure and energy density, they can exert external current, and what that really means that it provides a pressure support in the direction perpendicular to the magnetic field. And in addition, in the direction along the magnetic field, it has been shown that if the bulk of the cosmic rays, they travel through the plasma for faster than the Alfvén speed, which is a characteristic speed in the magnetized plasma, that will excite instabilities, and these instabilities can either drive turbulence, and they will exchange energy and momentum by wave-particle interaction. And these are the scientific focus of this talk. All right, so I will begin by introducing our new this code, which we call the MHD particle-in-cell, MHD-PIC approach, and how do we study this cosmic ray interaction with the gas. And then I will discuss about two applications. And they are both related to streaming instability. One non-resonant version, which is related to the acceleration of cosmic rays in shocks, and a resonant version, which is related to the propagation and self-confinement of the cosmic rays. Right. So to study the kinetic effects of plasmas, one generally has to involve particle-in-cell method, which is first principle. You treat all the particles as particles in your code, and which basically is the way you study plasma physics from first principle. For particle-in-cell simulation, well, this method is great, but there's a price that you have to pay, which is you have to resolve the tiny plasma scales. In the case of a so-called full PIC code, where you treat both electrons and ions as particles, and the scale you have to resolve is the so-called electron skin depths. And when you do that, you resolve all the physics, such as plasma oscillations, propagation of light waves, which in general you are not interested, but you have to resolve them anyways. You can also do the so-called hybrid-PIC approach, where you treat electrons as the massless conducting fluid, while you treat all the ions as particles. And in that way, you get rid of the small electron scale physics, but you still have to, you get all the ion scale physics. And in that case, you have to resolve this ion skin depth or ion inertial length scales. Both of them are still tiny plasma scales. This means in order to perform PIC simulations, it's very computationally expensive, and you are limited to use relatively small box, and you cannot run this for a very long time. For the problem of cosmic rays, most of the physics resulting from this interaction is the interaction between the cosmic rays and the gas. And the smallest scale that's relevant in this case is the gyro radius of the cosmic rays, okay, which are much larger than any of these small plasma scales of the background fluid. And so this motivates us to develop an alternative approach where we treat the background thermal plasma as a fluid described by magnetohydrodynamics, MHD, while we only treat the cosmic rays kinetically, same as particle in cell method. And in addition, because the interaction is mutual, we also include feedback from cosmic rays to gas. And by doing so, we completely bypass these tiny plasma scales that conventional PIC method have to resolve. But we also capture the full kinetic nature of the cosmic rays. And this will make this method computationally much, much cheaper. So just to very briefly how this works, okay, you have a grid-based MHD code where all the MHD quantities are defined in the cells, such as density, magnetic field, and velocities. And then you throw in some particles, and these individual particles represent, actually each particle, computational particle, represent a collection of real cosmic ray particles with the same properties. And in reality, what they really mean is that they represent a cloud of particles. And this cloud carries some shape, which is designed to facilitate interpolations. And then you basically push its particles based on the electromagnetic field that you read from your MHD grid. And in the meantime, the total energy and momentum of the system have to conserve. What this means is that you can have to do particle feedback from the particle to the background thermal gas, and this is done locally. Basically, any energy or momentum gained or lost by the particles is deposited back to the background fluid, so that the system is fully conservative. You may notice that MHD is intrinsically non-relativistic, right? So approximation is relativistic, but we can have relativistic particles in this prescription by just treating, we solve the full relativistic equation for the particles, and we do so by having it specify a numerical speed of light. As long as it's much larger than any MHD velocities, then the whole scheme is a consistent scheme. And then the full equations written in conservative form is just that, okay, this is the momentum equation written in conservative form for the background MHD. And then you add the source term, that is the Lorentz force on the cosmic rays, and with a negative sign. This is the source term for momentum equation. Similarly, you have a source term for energy equation. We have implemented this to the Athena MHD code, and this is described in the method paper that we published last year.
Nick?
Yeah.
Do you have a situation that the output speed is close to the speed of light, or you're far from that region?
Mostly we are far from, well, we are interested in applications that is far from that regime. We are still dealing with non-relativistic flows, but the particles can become relativistic. All right, so now moving to the first application, cosmic acceleration in shocks. So the origin of cosmic rays is mostly believed to come from shocks, and in particular shocks from supernova remnant. This is in fact a GIF file, and if you watch closely, you can see that this shock expands slowly. It's remarkable to watch how it expands. So it's from basically 2000 to 2015. And the basic physics behind particle acceleration in shocks is the first order Fermi mechanism, where when you have a shock, it automatically have a converging flow across the shock front, and if your particles can bounce back and forth across the shock front, they can gain energy in such a converging flow. But notice that if the shock is perfectly laminar, then because cosmic rays are collisionless, if the shock, there's no turbulence, the particle just travel along the magnetic field without doing anything. Right? In order to bounce and back, so you have this shock upstream that is flowing to the left, and this freshly accelerated cosmic rays that they can travel into the upstream to the right. And And this instability grows and to produce turbulence, and that will scatter your particles and make the process self-sustained. And the most relevant instability in this supernova remnant shock, which is a non-relativistic shock, but it's a high Mach number shock, is the so-called Bell instability. And the basic physics of this is illustrated as following. Let's say we stay in the upstream frame, and we have a background magnetic field. The fact that you have cosmic rays propagating through, streaming through, and these cosmic rays carry a current, okay? Let's say it's along the magnetic field. And because this is a high Mach number shock, the streaming velocity is much larger than the Alfvén speed. Well, let's say in the background configuration, the magnetic field is uniform, which means there's no total, the total current has to be 0. This means this cosmic ray current must induce a return current from the background thermal plasma. And what is this return? It is this return current that can drive the system unstable. And it can make so-called Alfvén waves unstable, but it's selective. So Alfvén waves can be decomposed into two. On the other hand, if it's left polarized, then this force, J cross delta B, will tend to suppress this wave. So it makes one wave unstable, and the other mode is suppressed. And fluid electrons, and which means in this code you need to resolve the ion skin depths. And this is a simulation done by my collaborators. What you do is that you collide a really fast plasma density, and bottom panel is magnetic field strength. And you can see that as the flow approaches the shock and they gradually becomes nonlinear, in the gas density, it tends to produce cavities at a certain point. And in the meantime, filaments. The standard parameter for this one is a parallel shock. Alfvén Mach number is 30. So everything is great, it's self-consistent. But this kind of simulation, they run this with 500 cores, and they run it for a month or MHD-PIC method, same parameter, and we also make the color scheme the same, just for comparison. And the resolution, just to compare, we use about 12 ion skin depths per cell versus you have to do 0.5 with hybrid. And you can see that overall the results are very similar. Okay, instability is filaments of magnetic field with. And just for comparison, we run this with much bigger box. So this is a box. This approach is that we need to artificially inject particles, because in this approach, particles into the acceleration process, and that we take from simulation. We calibrate that with upstream plasma that has been processed by the shock. We take about this amount and convert that into cosmic particles. This approach, we can also look at the particle energy spectrum. And so this is spectrum as a function of, so this spectrum is showing the y-axis. X-axis is the direction along the shock. This is where the shock is. And we measure the spectrum in the downstream. You can also see that in the upstream, there is a population of particles that goes all the way, travels through the upstream. And these are the particles responsible for exciting the Bell instability and make the turbulence. And if you measure the downstream spectrum, and so this shows the spectrum as a bunch of, see that over time, the maximum energy One unique thing that we can do in this code is that we can follow the particle acceleration process all the way to a relativistic regime. And to do so, what we do is that we set the speed of light, numerical speed of light, to be about 20 times the shock speed. And so that we can, so particles they start being non-relativistic, and then as the acceleration proceeds, they cross the they reach the relativistic velocities. And the stimulation shown here is more or less similar, but the shock travels at theoretical speed. But you see that it actually lags behind. This means that the shock starts to travel slower, and the reason for that the shock travels slower, which is something that we can obtain. And so this is the again the particle acceleration. On the bottom is the for regardless of whether you're in relativistic or non-relativistic scheme regime. And so this is P times 4 times Fp, so it should be flat. And we see that overall the shape is flat, and there's a slight change in normalization. But other than that, the acceleration continues smoothly from non-relativistic. The evolution of the maximum particle energy, okay, which is relevant to what is the maximum energy you can reach from these shocks. And for comparison, so this dashed line, this dashed dotted line, is the slope, basically rate of increase of the maximum particle energy when you obtain when all the particles are non-relativistic. You see that with relativistic particles, by the way, this is in our new simulation. This is beyond this value, all the particles are relativistic. So we see that first there's a slight reduction of the acceleration rate. This is because when particle becomes relativistic. And later on, there is a further reduction of the slope. And overall, the rate of acceleration is reduced by a factor of 2 in the relativistic regime compared with non-relativistic regime. And this further reduction is because of the saturation of the cosmic ray current. It's a little subtle. Basically, when all the particles are non-relativistic, right, as they gain energy through the process, they also carry more current, right, because their velocity increases, they carry more current. But when particles become non-relativistic, when they increase energy, the current no longer increase because their velocity is already c. This means when saturation of cosmic current means that you can no longer excite stronger Bell instability, and so that the acceleration becomes slower compared with non-relativistic case. All right, so this is the first application. Now we move to the second application, which is relevant to cosmic propagation and confinement. And the relevant instability is a resonant cosmic streaming instability. So when I say resonance, what kind of resonance am I talking about? I'm talking about a resonance. It's a gyro resonance of cosmic rays with circular polarized alpha waves. So this means that basically it means when particles gyrate around the magnetic field for one orbit, it also travels one wavelength along this wave. Because cosmic rays essentially move at the speed of light. So if you are a cosmic ray, you basically see this wave, which travels at alpha speed, basically doesn't move because c is much larger than VA. And so you can have forward traveling cosmic rays, which actually those particles are resonant with left polarized alpha waves. You can also have backward traveling particles, and they are resonant with the right polarized alpha waves. And if you go through all the algebra, what you will find is that when the bulk speed of the cosmic rays, okay, so all the particles, they are individual particles move at the speed of light. But the mean velocity of the cosmic rays, if that velocity, this drift velocity is faster than Alfvén speed, what happens is that its forward traveling particles will resonantly excite the right polarized forward traveling waves. Backward traveling cosmic rays will excite left polarized and again forward traveling waves, while backward traveling Alfvén waves will be suppressed. So that's what you find when you go through all the algebra. And the growth rate of this instability you can find is relatively straightforward. So this growth rate scales as the gyro frequency, or the cyclotron frequency of the cosmic rays, times the ratio of the cosmic ray number density that is in resonance over basically the number density of the background plasma, times, okay, how much you are faster than the Alfvén wave. Okay. And because of this factor, you can see that what's mostly responsible for this instability is the low energy cosmic rays, because they are the most abundant population of cosmic rays. This instability, have been studied in the 1960s and 1970s, where people have its linear properties and has been well known, and the quasi-linear theories have been developed, and that's it. And what we want to do is to really follow this instability all the way to the nonlinear stage to study its nonlinear saturation. But there's a challenge. And the main challenge, first, is that there's huge scale separation. So if you want to do this with a particle in cell code, well, you have to resolve, say, this ion skin depth. But this instability occurs on the resonant wavelength, which is, and you can, from these numbers, you can see for relativistic particles, lambda over the skin depth is about C over VA. And for conventional PIC, you have to resolve the ion skin depth, and you also have to accommodate this resonant wavelength, which is extremely computationally challenging. But for MHD-PIC, we don't have this problem because we don't need to resolve this plasma scales. And there is another challenge, which is because, well, this instability arises from resonant interaction, which means only a tiny fraction of population of particles, they are in resonance with the wave. Because particles travel in all directions, only a tiny fraction of that full distribution, they are in resonance with wave. Basically, so in order to capture this interaction, you have to use a huge number of particles per cell. And even with MHD-PIC, it is very challenging. And but we are able to alleviate this problem by implementing a so-called delta F method. Basically, instead of having all the particles representing the full F, if we know the background F, and now we just give them a different interpretation, we use particles to represent the perturbation of the distribution function, and that will greatly improve the signal to noise. And here's a very preliminary study of the 1D simulation of this cosmic streaming instability. So shown here, so everything is 1D. So this is 1D profile of the perpendicular magnetic field and perpendicular velocity. We start with white noise, okay? And so we can decompose. There are 4 wave modes. They're forward propagating, backward propagating, and they're left-right polarization. So they're 2 by 2. There are 4 modes. And we expect only forward propagating waves grow. And so the bottom panel is the wave amplitude as a function of k, and you can see that, so this means the backward propagating wave, and we can very well capture the linear growth of this instability. Well, we can see that the backward propagating waves, they are always suppressed. And we can measure the growth rate, and which basically they agree with linear expectations. Basically, it grows the fastest at the wavelength that is resonant with the lowest energy cosmic rays, and then they fall off on both ends. We can also follow this instability to the nonlinear stage, in which we have to employ some. We can follow the growth all the way to nonlinear. Okay, so it's still growing. Corresponding to conversion of Alfvén modes into compressible modes, and so on. So this is, again, just a very initial study, but the first time that we are able to simulate this instability from computers. Still, at the point where the system becomes nonlinear, our boundary condition where we continuously replenish particles from boundary becomes somewhat unrealistic, because at this point, all particles are very substantially scattered, but you're still injecting non-scattered particles from boundaries. But anyway, damping mechanism that will prevent the waves from linear stage, such as ion neutral damping, which we to see whether they are novel effects that incorporate cosmic rays. And in fact, cosmic rays are at the beginning of being incorporated into galaxy formation simulations, but all done in a very simplified manner. Either they include the if you just allow cosmic rays to be passively advected by the gas, basically this is a galaxy formation simulation, you get nothing. You just get a galaxy, nothing else interesting happens. But when you allow the cosmic rays to stream in, it generalizes with MHD simulations with anisotropic diffusion and so on. What we need to do is to use this microphysical simulation that I just described to provide a subgrid physics. All right, so to summarize, we have developed this MHD-PIC code that is valid on scales much larger than the plasma scales and is fully conservative. We apply this to study particle acceleration in shocks with general results agree well with previous more self-consistent hybrid-PIC simulations. And we can use very large box simulations and follow long-term evolution and follow particle acceleration from non-relativistic to the relativistic regime and see there's a reduction of acceleration rate. And in the future, we will try to improve the injection recipes, and we'll try to run this towards more realistic parameters. And we also use these simulations to study the resonant streaming instability. We have overcome a lot of computational challenges, but now we can confirm the linear growth rate, and we can continue to see this evolution into provide some prescriptions for the cosmic ray diffusion coefficients for subgrid models, such as in galaxy formation simulations. Thank you very much.
Okay, thank you. We have time for one quick question. Okay.
Can you use this new application to better resolve reconnection regions in global simulations?
Mainly a matter
So now, when we do the big switch, I can introduce our second speaker. So second speaker is Jeremy Drake, who almost doesn't need any introduction, but I still do it because I like to do this. So Jeremy is a senior astrophysicist in SAO, and he obtained his PhD from the University of Oxford. And before he joined SAO, he did postdocs both at University of Texas Austin and at University of California, Berkeley. And his main research interest, and as you will see and as you all know, is high energy astrophysics, and in particular stellar astrophysics. And his title, I think,
Thank you very much, Akash. So, blast. I don't think it's used so much in American English. So that's sort of a double entendre there. When it got a little bit worse, it would be damn and blast. And then if it was really bad, it would be damn blast. Here's Salvador Orlando from Palermo, Yanfei Zhang, who's just over here, and Sumner Starfield, and then the NOVA collaboration. There's a big Swift mass, peculiar and asymmetric. Why do the explosions, when we look at them spectroscopically and on the sky, not look like nice spherical explosions? novae. And if you don't know what the wobbly phase is in novae, I will get to that too. So first, Paul just said to me, I mean, I sort of said this in the abstract, so novoblasts are like the third. Now, novae are down there at maybe 10 to the minus 7 of the energy. You bother, and as Paul said, you know, it's like, you know, you got. But anyway, the thing is, the reason is that novae, you get to see everything. Maybe 1,000 years ago, and you get to see the nebula now, you get to see the remnant. It means because novae involves so much less energy, you get to see the whole thing, all the way from the initial explosion, all the way through the accreting white dwarf from maybe Roche-Lobe overflow in this. Nuclear reactions are ongoing. At some point, there's a critical density, and the whole thing just explodes. Overflow, there are also others, and this is not a very nice picture, but this is essentially supposed to be a representation of a symbiotic nova. So here we have a white dwarf orbiting in what is essentially the extended atmosphere of an evolved star. So it's accreting from the wind. It probably will not have an accretion disk looking like this, but will probably be a density enhancement along the orbital plane. It'll be accreting from that rather than through direct Roche-Lobe overflow from the star. So these are two types of novae that occur, and they have slightly different blast characteristics. So in principle, when the nova explodes, you should see something like you'll see in this green light curve here, a nice sort of smooth decline from a maximum. You see all this enormous zoo of behaviors, which is essentially a whole conference in itself, why this happens. So I won't go into those details, but just to say that novae are not well understood objects in these behaviors of the light curve, these cusps. So when you look at a nova explosion, you're essentially looking at the photosphere. When we see that light and the light decay, we're seeing how the photosphere of that nova essentially evolves. And it's not so much a luminosity decline that we're seeing, it's more of a temperature evolution. And that comes from the way that the mass loss from the surface of the burning layer on the white dwarf evolves. So the mass loss rate declines as it's thrown off mass. There's less material to burn, there's less material that gets thrown off. The mass loss rate declines, and so the photospheric layer that you're seeing the light from gradually shrinks down until it sort of gets down from the optic from those burning layers where there's still some steady nuclear burning going on. So there you have temperatures of about up to 500,000 degrees, and this is of course the famous supersoft source phase of novae that was first studied in detail by ROSAT and since then from all other X-ray observatories. So this represents a sort of supersoft source phase where you're seeing maybe 500,000 degree atmosphere, which is essentially a moving atmosphere. It's an outflow. More of that in a little bit. So after about 100 years or so, you have a nova remnant. You don't have to wait that long for the nova. The blue, the orange is knots in the remnant seen by Hubble Space. So the whole thing should look a little bit like this. It's a little bit of a crude animation, but the thing explodes. Essentially, the flame is spherical. Should take a maximum of a... So you should be left with this nice... and the shrinking photosphere thing, but... explosion from the white dwarf. The profiles do not look like they come from a spherical symmetric explosion. These are from an example from 1967, Nova Dell, Hutchins. So a spherically symmetric blast, if you just have a thin spherically expanding shell, uniform, it should have a nice sort of like square profile, right? Nice and square. Now you can imagine that this is sort of square, But, you know, it's quite different, isn't it? I mean, this one on the right, this is oxygen 3. Maybe you get a sort of bit of a square pedestal, but you also have this big lump sticking off the top. So this tells you that we're not looking at a simple spherically symmetric blast. Something else more complicated must be going on. And this happens time and time again in all observations of novae. In fact, most of them do not look like square profiles. There may be some square profile elements, but not square profiles. A more recent version, V339 Del from a few years ago, this profile, a bit of self-absorption, but again, nothing like a square-shaped profile that we would expect from a spherically expanded. And you deconvolve this using the fancy deconvolution HST algorithms, and you end up with something like this. Looks like a sort of, this one oxygen 3, this one neon 5, looks like sort of a bi-lobe thing with a blob in the middle. So explosion is intrinsically asymmetric, so maybe it just goes off on one piece of the white dwarf and that's it. It doesn't really work. Again, the timescales don't do that. A big effect on the remnant. Other things that have been proposed, jets. People, you know, you see these things written in papers. Well, maybe there's some jet activity. But what do you describe? Some sort of asymmetry. And of course, the third one, binary. Symbiotic nova. I mean, the obvious thing is that you're sitting in an offset r to the -2 density gradient, right? So you're not in the middle. So intrinsically, a blast wave from the middle, from the white dwarf, is not going to propagate equally in all directions. And especially, you might expect that the blast wave propagating in this direction is down the density gradient. It's going to go much quicker than the blast wave going back towards the star. So that gives you at least one plausible reason why you're not going to have a spherical explosion. So we decided that we were going to get together, me and Salvo Orlando from Palermo, and try and work this out once and for all and see what nova explosions really look like and start doing some detailed hydrodynamic simulations, which we used the flash code. So this particular one, RSO, so the red giant is here, white dwarf is here, and this thing here we put in, we took it out and put it in. It's a so the ejector, the bright stuff here, and you see the ejector, the red giant was down here, the white dwarf here, and we're just seeing that tilted now. So the ejector are strongly collimated in one particular direction. So the ejector mostly going in this direction. Density enhancement essentially carves out this part here. And if you look at it about now or a little bit after, that's exactly the point where you would get that two-lobe structure with a Roche lobe overflow novae. So this one is Sco, which is a nice system. It went off in 2010. It goes off about every 10 years. And it's an eclipsing system, so you can get some nice constraints on the geometry. We know what the orbit looks like. We know how big the stars are. And so we can see what an accretion disk and a nearby star does for you. This is the first minute or so of the explosion. And we see that the ejector in brown are blast wave. This is just showing the same simulation at coming in to the central region here. So again, a nice bilobe structure that develops fairly non-simple line profiles seen at different white dwarf orbiting at a distance of 5.5 AU or thereabouts. So here we have the center of the Mira. And this took a lot longer to evolve, so this was only done in 2 dimensions rather than 3. Looking structure up here. The blast wave instead does something really interesting. You see that it overtakes the giant and then concentrates behind the giant, and that's probably so moving on to one that's just gone off a couple of years ago, V745 Sco. Now this blue here is simply a it's an isodensity contour, essentially, an isodensity surface. So we have the again the star and the white dwarf is again a symbiotic nova. So white dwarf accreting from a wind rather than from a disk. So this is the equatorial density enhancement, and it's inside a 1 over r squared wind from the star. And the shock-heated blast wave propagating ahead of that. You also get reverse shock, the propagation. So again, a very highly collimated blast, certainly not producing a spherically synthetic X-ray. Did as many of them as we could, and they produced different X-ray morphologies. Some of them have this ring-like structure, which is produced by the equatorial density enhancement. Some of them have more strongly heated ejecta, which is what with our Chandra data, and that's what we show here. So the model. This is the silicon, magnesium, neon, and oxygen, hydrogen, lime, and alpha lines. Profiles are, first of all, they're pointy, right? They're pointy, they're not square, so we know that the blast is collimated. They're pointy and they're sort of more or less centered on 0 velocity, which means that most of the velocity component from the explosion was probably perpendicular to the line of sight on the plane of the sky. One thing explosion, and so oxygen is more easily absorbed than the other lines at shorter wavelengths, and so essentially the red-shifted part to the Chandra data, which enables us to constrain things like the ejector mass and the explosion energy. And you might think, well, show us some of the other simulations that don't work and match at all. So these simulations combined with X-ray observations can really give us some constraints on what the explosion probably looked like and what those explosion parameters. Okay, well, let's skip this because I can talk about it later if you want. Supernova progenitors. Best Supersoft source light curve that we had of a nova, V1974 SIG. I mean, remember Harvey once telling me that he didn't find this particularly interesting. And probably most of you who are looking at that like, well, that's not particularly very interesting. It all changed when Swift was launched. So Swift, of course, can do many observations of sources like this that last a long period of time. So this time, this is almost 2 years. So, Swift can cover these things with quite high frequency. Then RSOF went off, and this is what it looked like. So here we have the blast wave light curve here, and then that Supersoft source emergence. But it's not a nice, smooth emergence. It's jaggedy and toothy, and it goes up and down. It varies by factors of 10 on time scales of several hours. Factors of more than 10, in fact. Factors of up to 100 sometimes. And then it gradually starts to calm down and smooth on. This is where essentially the fuel is running out. Nuclear burning is getting less and less and less, and then the whole thing finally decays. This turned out to be not RSOF's peculiarity. It turned out to be almost the norm of all the Supersoft source phases that we were looking at. It wasn't ubiquitous, but it was very, very common. Nova Vol 2007, same sort of thing. Not such good coverage, but huge variations. Here, factors of 100 change in the X-ray flux. KT Eri, again, the same sort of thing. KT Eri going up down by factors of more than 100 in this early phase. And if you've seen me talk about KT Eri before, I'm not going to make that awful joke about KT Perry, okay? It's not going to happen. So we're not going to do that this time. Sco, that eclipsing system, a nice wobbly phase at the beginning. This is not wobbly phase. This is actually eclipses in the light curve as the Supersoft source got eclipsed by the companion. So wobbly phase in Sco, again, this is almost a ubiquitous behavior that we saw in Supersoft sources, almost ubiquitous. Why is it happening? Well, again, many explanations have been put forward. Absorption by unsteady nuclear burning. Maybe the nuclear burning layer is not steady. There's some sort of instability in the nuclear burning, and so your light is where you have a reforming accretion disk with sort of blobs in it that comes past and occults the source. Maybe it's something like that. Bizarre things going on, like photon bubbles forming, and becomes porous, and it's not a uniform sort of emitting layer. So somewhere I had this feeling that it must be something to do with radiation hydrodynamic simulations of massive stars. And he started talking about the ion opacity bump. And then I thought, damn it, that's what's going on. It's the ion opacity bump. And so you imagine here you're a photon coming up through the deeper layers of the star. You have a small opacity, then you hit this big bump. So suddenly you've got to start pushing really hard. This induces a density discontinuity or a density change in the atmosphere. And this whole thing becomes unstable. And if you imagine now coming at it from the other side, the shrinking photosphere as time goes on, as it gets toward this Supersoft source, is going through these stable layers, and then it's hitting this unstable layer due to the ion opacity bump. And then as it evolves further on, the photosphere recedes yet further, and again we're into steady waters, and that instability is no longer there. So this is a simulation of Yang phase. This is appropriate for a photosphere in which that temperature is similar to the opacity bump. And so it started out that's going to develop the instability due to this ion opacity bump. I forget what time stamp it actually starts, but anyway, there we go. So we have a very inhomogeneous bumpy. It's got pores in it. I wouldn't say Yanfei going on in there. If you look at the photosphere and how that photosphere is developing, surface. So this photosphere is going all over the place. And what's this doing? So this is essentially up and down. And so what are we seeing in the Supersoft into our X-ray bandpass, in the very softest part of the X-ray bandpass? So when the temperature by an enormous factor, simply because it's right on that vine tail and you're just moving Okay, so, but does it all work out? Does it really make sense? To do that, we need to sort of work out a critical thing, and one of that is, does this dynamical timescale it is? Fortunately, Sco comes to the rescue again because we saw its nice eclipse. Except it wasn't such a nice eclipse. So the top one, we have the epic PNXMM observation of Sco's eclipse. And look at that. That is ragged. The UV eclipse, on the other hand, is quite nice. Very nice and smooth. And so we work out the size of the object. Well, think not brighter regions that are fainter, and so the light curve is not going to look like a nice normal eclipse light curve. It's going to look ragged, just like this one does. But the geometry of this thing lets us work out what the mass loss rate is. We know what the radius is because we know it's eclipsing. We can work out the geometry. We know how big it is. We know, again, down to a time scale of 7 times 10 to the 4 seconds. So 7 times that, so like a chat after this talk, because it turns out that H0 might be a little problematic, but hopefully we'll sort that one out. In the Supersoft source, which is, since it's been observed 10 years ago, has been a great mystery in nova physics. So, summary. I hope I no other smoke and mirrors are needed. We don't even need magnetic fields to do this. We probably need them to do other parts of the observations that we can't explain with hydrogen. Surrounding the explosion, and we think we can explain all of these peculiar nova things using that. The SSS wobbly phase, I think, and Yanfei and I think that of massive stars. So, any questions? Small. I tried to work out, well, I did work out what they were. They were not anywhere near as prominent as the iron opacity peak. So yeah, the iron one is. The scale in the nova photosphere, that has to vary by several percent. Talk to you about that afterwards. Yeah, it wasn't a factor of 2, I don't think, was it, Yanfei?
Even the amplitude of oscillation?
Yeah.
See the movie, the not range of the neighbor, I say, for this particular case, of station, if the scale height is comparable to the radius, then you can actually vary a lot.
Yeah. Which is, I think, the case that we have, yeah. Oh, right. Okay. If you must. So, of course, they are relevant for the supernova question. Supernovae. But the main thing here is this delta M required to produce is that critical accreted mass as a function of the white dwarf mass here. And so it varies from this sort of few about 10 to the minus 3 at various aspects of those data on V745 Sco, including the hydrodynamic simulations, it's very difficult to get an ejector push the ejector mass above this value. Now, what we got here? We've got an ejector mass which is, well, you know, factors of at least several less than the mass gainer. We already know that it's really at the high end of the mass scale. It's close to Chandrasekhar limit already. If it's gaining mass, then inevitably it will have to be a supernova explosion if it's a CO white dwarf. We don't see any neon in the spectrum, so the indication